Challenges in chip manufacturing, technical aspects of chip production, and the future of the computer engineering. So, for introduction, chips are literally the unsung heroes of our modern world, powering everything for our day-to-day smartphones and laptops to high-power servers and advanced AI systems. These small, incredibly powerful components are found at the heart of nearly every device we use today and change how we live, work, and connect one another in fundamental ways. But how does it achieve that? It's a tale of extreme precision, built in microscopic dimensions and at the complex processes. This video goes inside the intricate world of chip manufacturing to reveal some of the challenges engineers must overcome and how photolithography and advanced fabrication create these mighty CPUs. We take an in-depth look at a few of the emerging trends in computer engineering for 2024, highlighting the leading innovations set to shape our digital future. Challenges in chip manufacturing. Why chip making is so hard? Manufacturing chips involves a lot of challenges, mainly because the chips are called upon to be smaller and more powerful with increased efficiency. This demand makes the manufacturing process change constantly at a very minute size, something that is inherently complex and costly. Reaching the precision that can allow further miniaturization of the main elements constituting a chip introduces physical and material bottlenecks. Shrinking these elements means immense expertise in technology but also puts considerable demands on resources, especially where the frontiers of traditional materials like silicon are reached. Recent high costs constitute one of the critical aspects in chip manufacturing. The industry is tethered to specialized machinery, such as lithography, which can engrave complicated circuitry into silicon wafers. Equipment can run up to plus $100 million for a single piece alone, meaning that only a few companies such as ASML are suitably equipped with machinery to make such machines, often monopolizing the most critical parts of its supply chain. It's a very specialized piece of equipment, and the rarity of its suppliers makes the whole industry extremely vulnerable to any disruption in supply chains, a fact that has brought the world to its knees. Besides this, a limited supply of raw materials, such as the rare earth metals used in the making of advanced grade chip, adds to these complexities. These are hard to mine and refine and have sources concentrated in certain parts of the world, further carrying geopolitical risks into the supply chain. Also, the fabrication facilities in Taiwan lend centrality to the risk of dependence upon a few key areas, especially at times of recent global tensions. Besides this, environmental and ethical challenges further complicate the issues. The whole process of manufacturing is extremely energy intensive. Clean rooms, precise temperature control, and huge amounts of water for cooling. This high usage of energy opens more questions about industrial sustainability and its footprint on the environment. More importantly, there are ethical concerns. Labor and the extraction of resources in regions where materials are mined create impediments related to worker safety and fairness. Chip manufacturing is an industry that compasses great feats and huge obstacles, the development of which depends on how successful it will be in finding its way out of this and complex problem. So, understanding photolithography. Some of the important processes in their making include photolithography and chip fabrication, which go into building these microchips running our day-to-day technology. It is a precise light-based technique for transferring intricate patterns onto silicon wafers to form billions of transistors. This process, invented in 1855, involves a mask of very specific design and a very powerful UV light that carves this design into a thin layer of photoresist with impressive precision at nanoscale. Masking materials and light are used to define structures critical to modern processors that enable high transistor density with increasing complexity in ever smaller spaces. So, understanding how CPU is made. From the raw materials to a fully functional CPU, the chip is charged into the extreme. From quartz and silicon, wafers are etched by melting and crystallizing pure silicon. The silicon wafers then undergo photolithography, whereby circuitry patterns are transferred onto them at radical levels of precision. Clean room environments are crucial here, maintained over 100,000 times cleaner than an operating room. since even the slightest contaminant can compromise intricate processes. Once the skeletal structure is laid down, doping, doping, a process in which some of silicon's atoms are replaced through ion implementation, changes its conductivity. This is a very critical step in the making of transistors that carry the electric signals correctly. Other steps, including etching and copper interconnects, allow the delineation of fine details in pathways between the transistors at a very small dimensions, enabling speed and functionality. This complex layering is part of what keeps Moore's law alive as density and performance climb exponentially with the transistors. Every added layer makes it even more complicated, hence a marvel of modern engineering. The final packaging stage makes it rugged and compatible. From photolithography to the final assembly, every stage has to be perfectly executed in delivering these powerful, tiny CPUs we rely on today. So, the future trends of the computer engineering profession. So, the field of computer engineering is considered one that has grown and continued to expand in the innovative use of technologies for the year 2024 and has reshaped the way we live for work. A few of them are this. So, number one is artificial intelligence. AI still leads the innovation in this spheres, from medical diagnosis to autonomous vehicles and even digital assistants. Hence, employers hire computer engineers who can use or implement machine learning into systems. Hence, a career path is dependent on expertise in AI. Its fast evolution depends on how much chip technology that can execute complex computations efficiently. For the next one is the quantum computing. It is a field of study that is now making its way from theory into practice, promising unparalleled computational powers in selected fields like cryptography and pharmaceutical development. That is why tech giants such as IBM and Google are putting resources into the study, making the need for computer engineers knowledgeable about quantum computing and proficient in algorithms resistant to quantum at an all-time high. This domain relies heavily on customized chip design to support extraordinary quantum mechanics. So for the next one is the Internet of Things. IoT is making day-to-day devices smarter, from home automation to industrial systems. This growing technology will need low power and efficient chip IoT devices that will support continuous data exchange and processing. Coupled with experience in embedded systems engineering, low latency chip design provides the best positioning for IoT growth. The next one is the blockchain. Although blockchain technology is quickly becoming more mature than straightforward cryptocurrency applications, from secure finance transactions, supply chains, and healthcare to even more, computer engineers that have cryptography and distributed computing development of workable secure systems that grow are needed. The need for secure, high throughput chips means advanced semiconductor technologies are instrumental in enabling blockchain technology. For the emerging fields, the edge computing, the need for real-time processing leads to edge computing, reducing latency by processing information at the edge rather than sitting it centrally in the cloud. A class of engineers who can provide design and specifications for energy-efficient, high-performance chips for edge applications will go a long way in having a major influence on this domain. For the next emerging field, which is the neuromorphic engineering, the novelty of these fields lies in the engineering of chips that would work exactly like the human brain. Neuromorphic engineering can revolutionize AI with dominant brain-inspired computing. So, its skills for the future. Computer engineers will be oriented to develop expertise in machine learning, quantum mechanics, embedded systems, and secure chip design to remain competitive. Since computer engineering represents the heart of the intersection with AI, IoT, and blockchain, engineers with such competences will be fundamental in defining new technologies, making them robust, scalable, and innovative. So, for the conclusion, as we have seen, chip manufacturing is an astonishing, although complex process from the precision at the micro level using photolithography to the intricate stages of fabrication that go into building a CPU. Every step shows how committed the industry is to pushing the edges of technology. And hence, with the need for smaller, quicker, and efficient chips, the need for constant innovation and resilience is driving especially in times of supply chain constraints and sustainability challenges. Looking ahead, this would also mean AI, quantum computing, IoT, among other up and coming areas like neuromorphic engineering, are going to really require creativity with chip technology. The future of our technical world no doubt depends on how well these challenges in manufacturing can be resolved. What it means is, as we forge ahead in better ways to design and manufacture chips, what we're really doing is opening new vistas across diverse industries, made possible not just by faster processors but by enabling those groundbreaking possibilities. So, thank you for watching.